Okay, here we are recording again. So I separated this into two parts because for some reason OBS just stopped recording audio after half an hour, and I continued talking for like another half an hour without knowing it. So I'm going to have to redo all of the stuff that I talked about. So that's neat. Anyway, all that I was saying about this particular example was that since we are taking horizontal slices in this case, because horizontal slices are that's what's required to get annular cross sections. This means that the variable of integration is now y instead of x. So the variable of integration is y, and y is ranging from 0 all the way up to 8. And you can see on the right there how you are in fact constructing the entire volume by taking all of those cross sections and adding up their volumes. The thing is, since the variable of integration is now y, we're going to have to take the equation y equals x cubed and solve it for x, so that it becomes instead x equals the cube root of y. Now, the inner radius is very clearly 0. The outer radius, on the other hand, is the distance from the y-axis to the curve. So that is the literal function value. That is the function that gives us this curve, which, since we've solved it, is y equals the cube root. Or, I'm sorry, x equals the cube root of y. So the inner radius is 0. The outer radius is this curve, which is cube root y. And that is indeed what I have said here in example 2. I then proceeded to do the actual problem. So here we have big R squared minus little r squared, and then I proceeded from there. But, I mean, that's all just power rule, so I hope that it is all straightforward. Okay, next, for example 3. So the region enclosed by the curves y equals x and y equals x squared, and then we rotate it about the x-axis. So let's take a look at this. What is this going to look like? So let me go ahead and get a fresh slate. Oops. So f of x equals x, g of x equals x squared. Now we are interested in the region between them. So that is for values of x between 0 and 1. So I'm going to isolate the bits that are between 0 and 1. And I need a comma, not a period. There we go. Turn those off. Open up the 3D Graphics tab. Now start up a slider to give the angle of the revolution. And make a surface associated with these two curves. And we are rotating it around the x-axis. Yeah. So there we go. We get this sort of horn-looking shape. So, do we take vertical cross-sections or horizontal cross-sections? Well, it seems clear to me that vertical cross-sections is what we need. So that means the variable of integration is going to be x. So we don't need to rewrite any of the equations that we've been given. So let's take a look at what these vertical slices are going to be. Let me start another slider. So the slices are going to range from x equals 0 to x equals 1. Okay, now the slice is going to go from the top to the bottom. And I've somehow managed to type things incorrectly. There we go. So here we see our slices. And if we rotate those slices, let me turn these off, you can see how indeed we get annuli as our cross sections, where the inner and the outer radius are functions of x. So, what is the... What did I do to make that turn off? Oh, okay. So as you can see, these annuli are what we get when we take a slice and then rotate that around. And indeed, the entire solid is composed of these slices. So you can see it's, yeah, slice is really the appropriate term here. We're cutting it into a whole bunch of little strips, and then adding up the volumes of those strips. So we need to know what the inner radius and the outer radius are. So let's take a look. The inner radius is the distance from the x-axis out to the line. So what is that distance? Well, it's literally the function. This function was f of x equals x, so the outer radius is literally just x. The inner radius is the distance from the x-axis to the parabola. So that means the inner radius is literally x squared, which is what we have here. So the outer radius is x, the inner radius is x squared. So then in the integral, we have big R squared minus little r squared. So don't forget that extra square that needs to go there. And then it just becomes another exercise in the power rule. Okay, next. So take the same region as in the previous example, but this time, instead of rotating it around one of the coordinate axes, we're going to rotate it around the horizontal line y equals 2. So let's take a look at what that looks like. So I don't want to get a completely fresh slate, because I need the same region. Let me keep this. Yeah, okay. So we've still got that. So now we're going to rotate it around the line y equals 2. So if you just type in y equals 2, GeoGebra will construct that line, and it gave it the name Q. So when you were creating the solid of revolution, now in this third slot, instead of putting one of the axes, you're going to put the name of the axis of rotation, which in this case, the name is just Q. So we have to do that for H and P, because those are the two bits that we are rotating. And let's see what that looks like. So, something like that. Something like that. So that's pretty cool. So, once again, we have to choose whether we are going to take vertical or horizontal cross sections. Well, it seems clear to me that vertical cross sections are what we need. So that means the variable of integration is going to be x, so we don't have to rewrite any of the functions that we were given. Now, as for the washers, well, let's see. So let's make another slider to represent the slices that we're going to be taking. If we're taking vertical slices, then the variable of integration is x, and that ranges from 0 up to 1. So here we have from 0 to 1. And then the slices themselves are going to go from h to p. Like so. So there's our slices. And then if we rotate those slices around, we get annuli. So there you go. Those are the representative approximating volumes that we get. Now, what are the inner and outer radii of this dude? So we have to be a little bit careful here, because the inner and outer radii of the washer, or of the annulus, are measured from the axis of rotation, which in this case is not one of the coordinate axes, it's just something else. So I think it's actually easier to see from the two-dimensional perspective. So the outer radius is the distance from the axis of rotation to the farther end of the slice. The inner radius is the distance from the axis of rotation to the closer end of the slice. So the axis of rotation is at 2. So that means this distance, which is big R, is 2 minus this. And what is this? Well, that's the distance to the parabola, so that's x squared. So big R is 2 minus x squared. 2 minus x squared. Okay? Similarly, the inner radius is 2